So welcome to the capacitance day 2 here. Remember yesterday we said that capacitance is just a new variable. It's measured in coulombs per volt, also known as a farad. I'll bet you could name that. Guess who that's named after? Okay, probably Michael Faraday, right? Okay. And so because it's Q over V, that means that since V always seems to depend on the geometric configuration of your charges, then C would also depend on that. In other words, different shaped plates and different shaped objects would yield different capacitances. So we actually have, I said yesterday we have parallel plate capacitors. We have cylindrical, more tubular looking capacitors. We have even spherical capacitors. I did a little bit of research over the lunch break just on the different kinds of capacitors. There are also supercapacitors that use a slightly more advanced technology, and they can have hundreds of times more capacitance than your typical circuit capacitors. So that's kind of a fun thing to look up. Try looking up supercapacitors, and it will tell you why they're called super. So we have superconductors and we have supercapacitors. Totally different though. Okay, since V is dependent on the charge configuration, C is also. And also, by the way, we can use Gauss's law to find field, E, right? And then we can use integration with a negative to get the V. And then we can use the C equals ice cream cone, C equals Q over V, to get C. So in other words, it's kind of a chain of work, but you'd first find E and then convert it to V, and then C over Q over that would give you your capacitance. Okay, so there's 3 basic cases I want to do. I want to do the parallel plate, and then the cylindrical, and then the spherical case. Okay, so in the case of the parallel plate capacitor, you have 2 plates, oppositely charged, equally and oppositely charged usually. Although sometimes they do use an asymmetric kind of thing, where they purposely make it non-symmetric. Then cylindrical capacitor, where you have 2 shells, 2 cylindrical shells. And then we have 2 spheres. Now these are naturally conducting objects, right? I mean, that's part of the deal. If you're going to be using capacitors, we usually use conductors for that kind of stuff. And so let's just look at the first case. If you kind of go back to Gauss's law, this has been a while now, and you just look at a plate, we usually draw a little cylinder protruding through the plate like this, also known as a Gaussian pillbox. I kid you not, pillbox. So you look at this little Gaussian pillbox, and you probably remember that the charge enclosed is epsilon naught times the integration of E dot dA. So it's been a long time since we did Gauss's law, but here it is again. And basically, we said that because of the Gaussian pillbox we drew, the E field, oh, by the way, we treat these field lines as straight. There's some fringing, that happens, but usually the plates are so close together and they're fairly big compared to their gap that you can just ignore fringing effects of the electric field around the edges and just treat it like a full-on parallel line situation, okay? So we're just going to do that. We're going to assume that then as you pick different areas across this top surface, as you pick different patches of area on this little red circle, that the field doesn't vary across here. So the field doesn't really change as you walk through this the top of this pillbox, okay? So that gives us permission. First we'll do the dot product, then we'll pull the E out, is what I'm saying. So the dot product is the area vector is pointing straight up. The E field is pointing either straight up or straight down, so it's a little bit hard to say, but the cosine is either 0 or 1, theta is either 0 or 180, depending on which plate is positively charged. But either way, you get a 1 or a negative 1 from your dot product. So it becomes Q enclosed equals epsilon naught times integral of EA cos theta, EDA, excuse me, EDA cos theta. My mouse just froze. There it goes. The E pulls out because we said that it doesn't matter where you are on the top lid, that feels the same. So the E pops out. And you're not doing a closed integral really because you don't care about the lateral faces. You only care about the two faces, right? You only care about above and below. So, and I'm sorry, you have field lines going downwards also that I never did draw. So let me draw those real quick. Those are going through the bottom of the pillbox. So anyway, you end up basically with a factor of 2 when you do this, if you remember. And so we have 2 areas. And then there's already a charge enclosed. That was provided by the battery, you know, or the power source. And so we've done this one before. You end up with basically E equals Q over 2 epsilon naught pi r squared. The 2 pi epsilon naught on the bottom, that right there is really 1 over 2k. So you could just write it as 2kq over r squared. 2kq over r squared. Okay, so the E field is 2kq over r squared, where r is the area of that pillbox. And that's your flux. And then the charge enclosed is, I'm sorry, it's not the whole plate. It's just that the part that's enclosed in our pillbox, actually. So there is a certain amount of charge in there, and that's going to be basically sigma times pi r squared. So you're going to have a sigma times pi r squared, and then your r squared is going to cancel out. So if you remember, the formula for the E field near a plate was 2k sigma pi. Do I need a pi there? Yeah, 2k pi sigma. Okay, so we have 2k pi sigma. And then if you go back to changing sigma to q over total area, if you change it to q over total area, now we're talking about the whole plate, you would get this. So you can leave it as a sigma or write it as 2k pi q over a. Okay, so if you replace the k with 1 over 4 pi epsilon naught, that might make more sense. So you'd have E equals 2 over 4 pi epsilon naught. Maybe I kind of regretted changing it to k in the first place. So then you can see this would be a 2, and you get q over 2 epsilon naught a. Okay, I think in the case of the infinite plate, we didn't have the a on the bottom, right? But this is a charged plate. I think we just had a sigma on top. I think we just put sigma up here. And so we could find, now that we're working with a finite plate and we're treating it as infinite case, we probably could just estimate sigma using q over a. So q over a, I'll just write it as sigma on top. Does this look familiar though? Sigma over 2 epsilon naught. That looks familiar. I think that's how we wrote it. Okay. That's just for one plate. There's 2 plates though, right? And since one plate is positively charged and the other plate is negatively charged, they set up equal and opposite fields, right? So the vector sum, if you're between the plates, you're going to get one field line pointing down, that comes from the top plate, and one field line pointing down from the bottom plate. So you actually need to double this to get the total field between the plates. Okay, so between the 2 plates, you would actually have double the field. E total is going to be basically sigma over 2 epsilon naught times 2. Okay, so we get sigma over epsilon naught. Simplest field ever between 2 plates. Pretty straightforward. Okay, now that's E. What about V? So V is the opposite of the integral of E dot ds. So what does that mean? Well, if you grab yourself one position on here, let's say it's the bottom plate, and you work your way to the top plate, you're going to travel a certain distance. Let's call that distance d. Okay? So as you travel along the graph, or as you travel upwards, the E field is pointing down, and the path you're taking is straight up, right? So you're going up, the field's coming down. So there's a 180-degree angle between you, right? And you end up with negative EDS cos 180. And that cos 180 provides an extra, it's EDS cos 180. That extra cos 180 is really just an extra negative 1 right there. So now this is a positive EDS. As you do move up, you notice the field doesn't change. The whole way along, the field is the same all the way through. There's no divergence of field lines. It's just like a nice straight line. So you can pop the E out again, and you end up with integral of ds. And what do you call integral of ds? If you're integrating from s equals 0 to s equals d, it's just d. So V is equal to ED for a parallel plate capacitor. V is equal to ED. And E is a constant, and D is a constant, and V is a constant. It's a very simple case. Okay, so now that we know that V is ED, let's go back to our capacitance equation. What was the capacitance equation? So far we have V equals ED for this thing, right? We had E is sigma over epsilon naught, total E field, right? What else we got? Capacitance is ice cream cone. It looks like an ice cream cone, remember? Okay, so our goal was to find capacitance today, and we have Q over ED. That's one way to write it, Q over ED. Or if you want to, you can think of the Q as sigma times the total area of the plate. So imagine that the whole area of the plate is A, right? And it's probably a square or a rectangle. And then E we said was sigma over epsilon naught D. So I'm replacing the E right here with sigma over epsilon naught. Then the sigmas cancel out, which is interesting. The capacitance does not depend on the charge density. And we end up with a purely geometric equation. This is so cool. It's literally A epsilon naught over D. A epsilon naught over D. And this is the capacitance of a parallel plate capacitor. You can write it as Q over V. You can write it as Q over ED. You can write it as A epsilon naught over D. They're all equivalent. And what's interesting about this to me is there's no Q anywhere. There's no charge. There's no voltage. This is purely a geometric equation. Your capacitance depends solely on the area of the plates. It is completely directly proportional to the area of the plates. And it is inversely proportional how far apart they are. So think with me here. If I make A twice as big, if I double A, then I double my capacitance. So that tells you double your plate size, double your capacitance. If I can't double the plates, maybe I just can't do it. Just can't do it practically. I don't have enough metal. That's fine. Move the D to make it half D. Shrink the D to half D. This also doubles the capacitance, you see? So some capacitors that you'll read about, if you especially look up those supercapacitors I mentioned, you'll see that the D value is very, very, very small. I'm talking about like manufactured to where the plates are so close together. That maximizes capacitance. And also they make as much area as possible. They wrap these sheets around into cylinders and they try to get them as close together and as big as possible. Okay, epsilon naught is going to change later when we fill the capacitor with a different chemical. So if we don't want air or vacuum to be between the plates, we can fill the surrounding space with a different medium, and that can cause a better capacitance as well. So that epsilon naught will increase its value as well. All right, now the cylindrical case is very similar, but instead of re-deriving with Gauss's law the field of a cylindrical case, we're just going to steal it from the book. So Gauss's law basically says Q enclosed equals, right, epsilon naught times the closed integral of E dot dA, right? The Gaussian surface we'll pick is a cylinder of its own, another pillbox, but this time the flux is through the lateral face. And so we already did this before, actually more than once. We actually got for the surface area 2 pi RL. It's like a rectangle. And there was the E being constant no matter where you were on the shell part of your red there. So the E pops out of the integral, and you end up with a dot product of 1 again, or the cosine theta is cosine 0, and then there's an epsilon naught. So we didn't go through it carefully, but this is what we had the last time we did this exercise. And now we're going to take this field to be Q enclosed. And in this case, what's cool about this arrangement is technically the G surface we drew encloses all of the capacitor, unlike the last example. In the last example, our little pill box only enclosed part of the total charge. But this thing covers the whole charge. You can see it's as tall as the capacitor, right? So I could just use capital Q if I wanted to. The total enclosed charge is capital Q. It's the whole charge. So I'll start there. We have 2 pi RL E epsilon naught. And then isolating E, like we did last time, we have Q over 2 pi RL epsilon naught. Okay? And now, you might ask, well, what about the field coming from the outer shell? 0. 0. Remember last time we had a plate above and a plate below? They both contributed to E field. But we are inside a conductor here. No field contributed by the outer shell. Interesting. So we're not going to double this time. What we are going to do is integrate it, though. So this R is technically a lowercase r. Mr. Shore should have used a lowercase r right here. Okay. And so I need to fix that real quick. Where's my eraser tool? There it is. This is supposed to be a little r because it's the radius of the G surface, technically. It's the radius of the G surface. Okay? So the surface area of the G surface is 2 pi RL, not 2 pi capital RL. All right, now what's going on with our potential function? So the potential is the opposite of the integral of, remember this? V is the opposite of the integral of E ds. So the field points perpendicular to every shell. It's a radial field. And we're going to travel from the inner surface to the outer surface. So we're going to do our little journey, our little ds journey in the same direction as the E field. So the theta will be 0, which means you can just simplify E dot ds as just E ds. So you don't need a dot product when the theta is 0. You cannot say that along your journey the field doesn't change. That's a lie. As you go further away from the cylinder, your field does change. These field lines are not, they're not like the forest of trees we saw in the parallel plate. They are actually diverging as you leave. So unfortunately, we can't just pull the E out, but we do know the E. We just wrote it down. We just had it right here. So we'll steal it, but we're not going to just pull out the E. Okay, so it's going to look like this now. V is equal to negative integral Q over 2 pi RL epsilon naught ds. And we're interested in integrating from the inner shell to the outer shell. So we'll call the inner shell radius A, and we'll call the outer shell radius B, like this. Okay, the Q pulls out, the 2 pi R pulls out, the L pulls out, no, sorry, the Q pulls out, the 2 pi, the L, and the epsilon naught. They all come outside because they're all constants. Okay, so it's going to look like this. Oops. It's going to be V equals negative of, and then a bunch of stuff outside. So we have a Q, we said, there's a 2 pi, there's an L, there's an epsilon naught. And we're just left with 1 over R ds. And ds is dr. Like as we make a slight motion away from the center, that is both a dr and a ds, technically. So we could actually change this to a dr as well. So I was a little informal with that step. I probably should have caught that earlier. All right, so we just end up with this simple integral from a to b of 1 over r dr. That's just ln r. Technically, it's ln absolute value r, but this is geometry, folks. There's no negative r's. So you just end up with this negative q over 2 pi L epsilon naught and then you end up with ln b minus ln a. Or if you like to combine your logs, ln b over a. Okay? So if you like to put your logs together. I don't care which one you use. This is for a parallel plate. And if you want to call it 2k q over L, you can also replace the q. So that's what I'm going to do right now. I'm going to finish this video. I'm going to replace this q with sigma, you know what I mean, over sigma a. And a lot of this is going to cancel out, and it'll look a little different when I'm done. So you could write it either way. There's other ways to write it too, though, because remember the q is the charge on the capacitor, which means really the charge of the positive plate of the capacitor. We talked about that yesterday. Charge on a capacitor just means charge on one plate of the capacitor. I'm kind of assuming that our field lines are radiating outwards. So that's kind of the way that I had drawn it. And so actually when I integrated, I did from basically the inner to the outer, like that. Okay, so, but we're really looking at the surface charge on here, on the inner cylinder, and technically that surface area, remember, was a rectangle. If you unwrap it, it's a rectangle of size 2 pi r L, and it's the inner one, so it's 2 pi a L, 2 pi a L. All right, so if you kind of just go back to the equation, you could rewrite it a couple more times. I always like to do that. So let's do that real quick, just so we have multiple versions. So we could write V equals, instead of Q, we could put negative sigma times 2 pi AL all over 2 pi L epsilon naught. And then this is times ln B over A. And then you'll see that some things cancel out, like the 2 pi's gone, the L's gone. And that's kind of a nice way to write your V. So this is negative sigma over epsilon naught ln B over A, like that. That's definitely a nice clean way to write it. Sigma, if you don't want sigma in there, because technically you probably won't know sigma that often, you could get away with leaving it as Q, actually. But remember, we're not trying to study potential. We're actually studying the capacitance, right? So we're not quite done anyway. We have to take our C, which is ice cream cone, and we would put basically Q over, and we get to pick whichever potential equation we like to look at. Why not pick the first one? It had a Q in it anyway. So we could put our little Q over 2 pi L epsilon naught ln B over A. And then the Q's cancel out. And let's see, there's a negative. Mr. Shore must have an error here somewhere because he has an extra negative. I think I'll catch it in a minute. Just give me a second to clean this up. Okay, so you just end up with basically 2 pi L epsilon naught all over ln B over A. Okay, that's for the cylindrical capacitor, and it includes things that we would know, like the L. We would know the length of our capacitor. By the way, the L is truly the length of the capacitor, right? B and A, we wouldn't know it when we buy a capacitor, but if we design a capacitor, we would know the distance, the radii B and A. Okay. Okay, so Mr. Shore has a negative that's kind of floating around here in his potential function, and that showed up in my C. We cannot have a negative capacitance, so I just need to double check my work. Let's see here. We went, I think it's the direction I integrated, so anyway, I integrated from the inside to the outside, and technically the ds then is the same as dr, I said, and Okay, I'm not too sure. I'm not too sure which one what I did wrong. So anyway, we certainly wouldn't want a negative capacitance. There is a negative error. Maybe you can help me catch it. But anyway, the book liked to integrate from the outside to the inward shell. So like they went from the blue ring down into the red ring. I went the other way, but that's definitely where my mistake is. But I was supposed to integrate from the outside in, and they integrated from the inside out. But then they used an extra negative. I'm not sure. Okay, so anyway, see if you can find it. Maybe it'll pop out to me here in a minute when I do the spherical case, and I'll come back and fix this one. Okay, the spherical case is actually, you'd think it's like really complicated, right? But actually, if you remember, the spherical case is the simplest of all cases because we treat spheres as point charges. So if you draw a Gaussian surface around this, it might as well be a Gaussian sphere. And that Gaussian sphere, if you look at epsilon, charge enclosed, excuse me, the charge enclosed on our spherical plate should equal epsilon naught times the integral, the closed integral of E dot dA, right? But remember, especially if this is a positively charged plate, the E field lines are pointing straight out. The normal vector is pointing straight out, so the area and the E field are definitely well aligned here for all area patches surrounding the Gaussian surface. So theta is always 0 no matter what we do. So that simplifies the dot product to simply EDA, cos 0, or EDA. The E field doesn't change as you traverse across the patches. So, it does change as you move away from the center of the sphere, but as you move around the shells, the Gaussian surface, you don't experience new values of E, right? Only if you move away from the central ball. Okay, so the E pops out again. The E pops out. And then we just have the integral of dA. So that just means the sum of all area patches on the entire G surface. And that's, of course, 4 pi r squared. So we basically end up with epsilon naught E times 4 pi r squared. Now we're going to have two shells here. We're going to have two shells. We're going to have the inner shell and the outer shell. Mr. Shore doesn't want to use A or B yet. I'm sorry. This is the radius of the red G surface. Yeah, I got to be careful here. This is the area of the G surface, not the area of the little blue ball inside it. Okay, this is supposed to equal Q enclosed, as you know. So then E is going to equal Q enclosed. Well, all the charges enclosed. So I'm going to treat Q enclosed as just capital Q. So it's going to basically be capital Q all over, and then I'm going to have a 4 pi epsilon naught r squared. Okay, this is enclosed in our G surface. Enclosed in our G surface. So our goal now is to take this, and we're going to opposite integrate it. So integrate it and put an opposite on it. So V is going to be, oh, by the way, this is an R hat, right? I keep forgetting to write directions on my E's here. When we integrate, we use a mandatory negative. Ah, that's what I forgot up here. Ah, yes. Oh, no, there was a negative there. I did remember my mandatory negative on my E field integration here. When you integrate E, you are supposed to use a negative there. I was supposed to put two negatives on this. I'll come back later. We'll find it, hopefully. So anyway, it's integral of E dot ds. And then basically what's going on is you're integrating from one spherical shell to the other spherical shell. So you're going to be integrating, and I think they like to integrate from the negative object to the positive object. I think that's why maybe I'm getting a negative error. I'm integrating from the positive object out to the negative. They like to integrate from the negative object down into the positive object. It seems kind of arbitrary to me because who's to say we should build our capacitor with the negative charged plate outside anyway. But anyway, these are the two. We're done with the Gaussian surface, so I think I'll stop using red. Basically, there are two shells. Oh, and by the way, why did we not double our E field? Don't we experience E field from both spheres? The answer is no. We do not experience any E field from the outer sphere, only from the inner sphere. So technically don't double this E like we did in the parallel plate capacitor. So both in the cylindrical and the spherical case, we do not double the E before we integrate. Okay, and now going to the integration. Oh, and we're going to be going, let's follow their convention. We'll go from the negative object, which they're saying is on the outside, to the positive object, which is on the inside. So if we integrate that way, we're going to be going from shell B to shell A. So B is the bigger shell, A is the little shell. So we're going to integrate from B to A, like that. And technically, ds is the direction we're going to travel. So we're going to travel inward. So ds and dr are oppositely oriented. So dr obviously points radially out, but we're traveling radially in. Okay, so ds and dr are oppositely oriented. Okay, so I'm going to replace the dr with a negative ds, basically. Or I should say the ds with a negative dr. So it's going to look like this. This will be a positive. This is a B, an A, and an E field. Oh, and the theta is exactly 180. That produces another negative. Okay. So let me show my work. It's getting kind of confusing here. So I still think that directions are arbitrary, but as long as you report a positive capacitance in the end, I'm sure it's correct. So anyway, I was going to do one more step in here just to avoid any further confusion. So we have EDS cos 180. Cos 180 is -1, so we have positive integral EDS. The E field changes as we move away from one shell to the other. So it is a divergent E field, like we actually have field lines getting more dense. So we cannot just pull the E out of the integral, unfortunately. But up here we do have the E field. It's Q over 4 pi epsilon naught R squared. Or you could just think of it as KQ over R squared. So we're going to stick that in here. And we're going from B to A. So we basically have V equals integral from B to A, 1 over 4 pi epsilon naught times Q over R squared. And this is ds, but we said already that we're about to change that to a negative dr. We don't need vectors anymore. We already dot product. We already did our dot product. Oh boy, it's a lot of work, isn't it? Okay, so we end up with V equals integral B to A, and we have 1 over 4 pi epsilon naught, and it's basically QdR. Another negatives got picked up because ds is negative dr, and this is all over r squared. Okay, so pulling everything out of the integral that we don't need, we have basically a negative q over 4 pi epsilon naught. And then this is integral from b to a of dr over r squared. And thinking of this as r to the minus 2, we'll anti-derive, we'll add a power, we'll put an r to the minus 1 power, we'll do a 1 over negative 1 in the front. You remember the drill from calc class. We end up with negative r to the minus 1 plus a constant, but we're doing a definite integral. So it's basically negative 1 over r is our antiderivative. Then this negative, don't you love the negatives in physics? This negative cancels with this negative, so now V is positive again. And it's Q over 4 pi epsilon naught, and we have basically 1 over R. We're evaluating from B to A, and we end up with V equals Q over 4 pi epsilon naught, and then we have 1 over A minus 1 over B, and combining the fractions, we have B minus A over AB. Okay, and then this is 4 pi epsilon naught. I kind of just wish we could use a Q here, but it is, I mean a K. It is nice to have epsilon naught because finally epsilon naught's going to mean something here soon. Okay, almost done. Ugh. Now the ice cream cone. C is Q over V. So we have, here we go. Q over 4 pi epsilon naught times B minus A over A minus times AB. And the Q's cancel, and we get 4 pi epsilon naught. Oh, I need more room. We get the capacitance of a spherical capacitor is finally 4 pi epsilon naught times the reciprocal of B minus A over AB, or you could say AB over B minus A. You'll notice that every one of these capacitances are only geometric. There is nothing about them that indicates charge density or anything else. They're all 100% geometric. So there you have it, the three most basic capacitor configurations. Next thing we're going to do is build circuits from these. Wow, I still never caught my negative. I'm going to go back here real quick. If we insist on their convention that we integrate from the negatively charged outer object to the positively charged inner object, then technically my ds here, when I changed it, it would be a negative dr. And that means that this would have been a positive here. I'll highlight it in blue, actually. That would be a positive. That would be a positive, so let's fix it. And then this would be a positive. And this would be a positive, which makes my final capacitance positive. As I wrote, I never did carry the negative from my V. So I was afraid to, but now I found my mistake. So anyway, you know, which plate you go from and to, I mean, it matters, I guess, but in the end, you know, who's to say you're supposed to put the positive plate on the inside, or on the inside, and then have it radiate field lines outwards? Like, what's the rule on that? I mean, who said you can't just switch the plates? So anyway, capacitances, I'm going to label all three and put them all together. Okay, so we have, let me just kind of find a blank spot. We have capacitance for a parallel plate, which is our most commonly used one probably because it's the simplest. And that was simply epsilon naught times the area of the plate divided by d. So the area of the plate times the, and then this is d, the distance between them. So that's the first one. Let me put the little picture with that. Then we have the cylindrical idea. We have nested cylinders, and this provides a nice capacitance. That one was way more complicated, but the final way we wrote it was 2 pi epsilon naught L all over ln b over a. And there's not really any way to bring that ln to the top. But again, purely geometric. L is the length of our cylinder, and a and b are the radii of the two cylindrical shells we made with metal, or whatever it is. And then next is the spherical case. And so for the spherical case, let me shrink this down a little bit. That's a ball within a ball, like this. Again, radius A and radius B. And that one came out to be 4 pi epsilon naught. And then it was AB over B minus A. Obviously, if you're trying to decide if it's A minus B or B minus A, just remember that we need a positive capacitance. So you have to do B minus A, actually. Okay, so they all have an epsilon naught. One last comment. I've said this before, but I'm going to say it again. The capacitance does depend on geometric things, but there's this other little epsilon naught that just keeps popping up in every one of these. And so if we could somehow increase epsilon naught, we could store more charge on our capacitor plates per volt applied. See that? So that actually is one of the strategies to increase capacitance, is to change epsilon naught from the vacuum permittivity to a dielectric permittivity. So we would want to increase this if possible, and sticking goo of some kind between these plates can increase our capacitance. All right, and there's more than one way to accomplish that. So anyway, that's a research topic for another time. Hope you enjoyed the capacitance video.